Up to this point, we have practiced graphing the inequalities, we have practiced shading the appropriate place, which is called the feasible region, and we have practiced finding the corners. So the last part of this, except for making an entire problem from start to finish, is finding the objective function and using it to find a maximum or a minimum. To start these problems, you just go ahead and graph the equations, just like we've been doing. So go ahead and take a moment and take those inequalities and graph them, and then we'll come back and talk about the rest. Now that we have it graphed and we can see that the feasible region is where I have colored it purple, we have to find the corners of this feasible region, which are 1, 2, 3, 4 points. So we'll go ahead and write down those points. So those points are 0, 0, 0, 90, 120, 60, and 150, 0. Now what we're going to do is we're going to take those points that we have found and we're going to plug them into our objective function. Before I scroll back down, I'm going to look to see, so we're finding the maximum or the highest value possible. So 10x plus 15y we're going to plug those numbers in. So 10 times 0 plus 15 times 0 is 0. 10 times 0 plus 15 times 90 is 1350. 10 times 120 plus 15 times 60. Let me plug that one into my calculator. So 1200 plus 15 times 60 is 2100. 10 times 150 plus 15 times 0 is 1500. And then we're looking for the maximum amount. We don't know what they're maximizing, if they're maximizing profit or amount of materials, but the highest value that we have here is 2100, and we don't even know what this 2100 is representing. But we do know that at 2100 they should have 120 of whatever the x variable is standing for and 60 of whatever the y variable is standing for. So that's what they're going to do to maximize that objective function. Go ahead and look at the next one. So this time we are also maximizing. Here's my objective function, here's my inequalities. So we're going to go ahead and graph, just like before. That's always what we start with. So here is our feasible region. And so I'm going to pull out the corners. So my corners are here at 30. And I have another one down here, and if I would have drawn a really nice straight line, I would have been able to see that they do cross at this point of 16.6, and I really don't know why my pen keeps going out. And then 30, 32, 34, 36, 38, and I can see that it crosses here at 40. Now what's happening is these actually are going forever in both directions. So this is an unbounded region because it's going forever above. But those are the 3 points that I'm going to use. So I'm going to draw my chart. So I have 40, 0. I have 16, 6. And I have 0, 30. So I'm going to go ahead and go up and grab my function. 5x plus 10y is my objective function. So 5 times 40 plus 10 times 0. 5 times 40, so we got 200. We have 5 times 16 plus 10 times 6. 5 times 16 plus 60 makes 140. 5 times 0 plus 10 times 30 equals 300. Now this problem is asking for the maximum. So in these corner points, this would be considered my maximum. But really this question shouldn't be asking us for maximum, because if we think about it, let's go back up and look at the picture. Remember, the shaded region are all the possible answers. So these are just the corners or the options, but any of these points, anywhere along here, and even the ones in the middle, because I'm going by twos, so I've got points in between here and here. I have all of these other points. Most of these are going to give a number that is higher than what I have given here. This type of problem, because it's unbounded up above, really should be doing a minimum problem. But if it did ask you for maximum, you would say there is no maximum, because I can't give an upper bound on this one. It goes forever. Okay? This would be better off to be a minimum problem, and if that were true, then your answer would have been at 16.6, because that is the minimum. But they were asking for maximum, so we'll say there isn't one. Okay, so now let's go ahead and look at this next one, which is on multiple pages. So I'm going to just real quick stick it on one page. And we're going to go ahead and just get it set up for today. We'll get it finished on Monday, but we'll at least get it set up. Mom's old-fashioned casseroles produce a luncheon casserole that consists of 50% carbohydrates, 30% protein, and 20% fat. The dinner casserole consists of 75% carbs, 20% protein, 5% fat. The luncheon casserole costs $1.50 per pound, and the dinner casserole costs $2.50 per pound. How much of each type of casserole should be used to provide at least 3 pounds of carbs, 1.5 pounds of protein, and half a pound of fat at a minimum cost? So if we're trying to get a certain amount for nutrition-wise, but we don't want to have a lot of money out, that's what we're focused on here. First thing we need to do is come up with our variables. So since we're focused on making, and here this will help sometimes, if you read the question of what they're trying to get you to solve, how much of each type of casserole? Well, our two types of casserole are luncheon and dinner casserole. And what we're focused on is how many of the luncheons and how many of the dinner casseroles should I make. Now the next thing you should do is find the objective function, or the z equals equation. You want to do that so that you don't accidentally use it in the constraints. They are asking us to find the minimum cost, so any numbers that deal with cost need to be used in this objective function. So my cost would be my dollar amounts. It says a luncheon casserole is $1.50 and a dinner casserole is $2.50. So these are my objective functions. So now I'm done with these numbers. I won't use them again. We're going to use the rest of the numbers to make the constraints. And as we're reading this, we notice that we are three things that we're focusing on. We're focusing on carbs, protein, and fat. So we're going to have one inequality for each one of those. Our percentages we're going to make as decimals. We're not going to leave them as percentages. So our carbs, our luncheon casserole is 50% carbs, so that's 0.5x. Our dinner casserole is 75% carbs, so that's 0.75y. And it's at least. Now, at least is a minimum, so everything has to be greater than or equal to. And in this case, it's 3 pounds of carbs. So my 50%'s gone, my 75%'s gone, and my 3 pounds is done. So those three are all done. Now I'm going to protein. So I have 30% protein. I have 20% protein. And my protein needs to be at least 1.5 pounds. So those numbers are done. Then I have my fat numbers. So I have 0.2x plus 0.05y is greater than or equal to half a pound of fat. Okay, so you just kind of scan through the problem. Is there any other numbers left? And there's not. Now the only other thing you need to think about is, can you have a negative amount of pounds of luncheon casserole and dinner casserole? And the answer is no. When you're making a product, it has to be, you can do 0, but you can't do negatives. So the last constraints that we're going to actually have is x has to be greater than or equal to 0, and y has to be greater than or equal to 0. So these are our constraints. So on Monday, we're going to go ahead and we'll actually finish solving this problem. Have a good weekend.